Yeah, I'll do with the keyboard. I think I'll use this. Okay. All right, so let's get started. So let me first recap what we did yesterday. So if you had the courage to follow me, I hope you managed to code up this, which is nothing but copy and paste. That's very minimal. You can copy and paste thing on a Jupyter notebook. And I claim that these two things here are essentially all you need to know about a normalizing flow, at least from the basics. Okay. So that's sort of the beginning. There are way many things that we need to discuss to make this thing useful for you. So I need to change a little bit the outline of this, but let's keep continuing the discussion. So the primary thing that I want to talk at the beginning today is how to train that model that we discussed yesterday. And this is a critical part that you need to sort of understand. So just to recap conceptually, like what a normalizing flow does for you, you basically provide an array that you sample from a Gaussian. You pass to the normalizing flow. Normalizing flow will give you an array of the same dimension that is mapping to a different space, but it will also give you the associated probability density for this sample. Okay, so a normalizing flow take an input, which is random numbers, and then it will convert into a PDF and the corresponding sample. Okay. So how do we train a neural net? That's basically problem dependent. And as to the extent of my understanding, there are technically only two ways that you can train this type of normalizing flow. So the first class of problems, or the class form of data that you might have, is when you have the actual probability density, when you have the density at your hand. So what are the examples of such? Suppose you have the analytic expression for your posterior distribution. In that case, this will be one way, this belongs to this class when you have a functional form for the PDF. Another possibility is that you want to sort of sample a differential cross-section for whatever reason. There are other ways of doing it, but let's say that you have some sophisticated differential cross-section computed at whatever orders in perturbation theory, and you want to convert that thing into event samples. Differential cross-section is also a probability. So you can, in principle, use the normalizing flow to train at the density level because you have the density. Another possibility is that you have in your hand an Euclidean action in lattice QCD, and you want to sample gauge configurations, and the Euclidean action is essentially a probability. So if you have the probability, then you have a data in this format, and the training goes into a certain way, as I will explain. Another possibility is that you don't have the PDF. What you have is just basically the samples. So for instance, experiment gave you phase-space samples, events. So event 1, event 2. This is an inclusive event. So let's say that an event consists of 5 features. I don't know what that event is. In the case of inclusive, EIS is the phase space of the electron, the X, P, Y, P, Z of the electron. So it will be 3-dimension, 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 and so on, so 4, right? So that in this case, I don't have a PDF. I know that these samples were drawn from some underlying PDF, but I don't have the PDF. And I will argue that you can still train a normalizing flow on the samples themselves. So depending on what kind of research you do, if you are more like working with events, yesterday Iris was talking to me about unfolding, well, that will be the space that you'll be working on because you don't know the PDF. But if you know the PDF, you'll be mostly in this setup. The examples exercise that I'm going to be playing with you will be mostly on this space. But I will argue in the next slides how to do something like this, okay? Now, we should do a little bit of a side note because, normalizing flows were not invented by our community, okay? It was invented by the machine learning community trying to create fake images. And so, as I just said, imagine that you have a case where you have these arrays, 5-dimensional arrays. It could be 10-dimensional arrays. It could be billion-dimensional arrays. It doesn't really matter, the dimension here. And so just imagine that you have a problem with 9 dimensions, okay? And you can sort of take this and reshape it into a 3x3, and that's technically an image. So the reason that people in imaging work with this was because they can actually cast the images as arrays. They can use this trick, okay? So if you decided to do images, then naturally this will be the place that where you want to work with. So this is just a side note that ultimately there is no magic about image generation. It's just arrays that you want to generate in multi-dimensions. Okay, so let's go back to the question of how do we train the neural net? I think maybe there are other possibilities, but the only possibility that I am more familiar with is to use the KL divergence. I literally copied this thing from Wikipedia. This is what is the KL divergence is. Here, the P is the true probability density, and the Q will be the fake probability density that you will encode into a normalizing flow. And this is a measure between two different densities. So you can see here that when P is equal to Q, this is 0. So you basically reach to the minimum. So if you want to sort of optimize a neural net, this normalizing flow, you can try to minimize the KL distance, namely minimize this quantity. I don't like to play with P and Q because it's a little bit confusing. So it's better to use, at least for me, to label one of the P's with T, meaning true, and the other guy with F, meaning fake. And that would be much easier to know what I'm talking about. So I just relabel this equation into this equation. Yes?
It would be easier for calculating that to use instead of, you have a logarithm and then you multiply it for a probability. To use this QF instead of PT. I don't know why it is multiplied, the logarithm by the other probability. Yeah. I think it's for kind of weight of the.
Yes. So this is, I have to be honest with you. I think that I didn't prepare myself to explain why this loss is good enough. But I will tell you why I do care about having this P here. And it will play an important role having this P here. And I will tell you in the next slide. So it turns out that depending on the form of data that you are tuning, you need to actually adjust that KL divergence. So if you are doing basically the samples, I will argue that you have to use the standard KLD as it stands. Okay, so let me just go back to the wiki. The wiki says that P, which is this guy, is here, and this is the true probability. Okay, and Q is the fake. So I will argue that if you want to train the normalizing flow just on the samples, you need to use the standard. Why is that? Because you need to actually carry out this multidimensional integration. This is an integration over the dimensions of your feature space. So if you are looking at 5-dimensional problem, that means you have to carry out this integration in 5 dimensions. If you have an image that is 100 by 100 pixels, that's a lot of pixels, this means that this integral is massively big, right? And how you're going to do that? Well, thankfully, I have this P here because I can apply Monte Carlo methods to integrate this function. So in order to do that, all you have to do is to sample from the true distributions and then evaluate that weighted integral as this. So I hope you appreciate that this integral, if I sample a vector of x from this PT, and I can actually approximate that integral just as this ordinary sum. Okay? Notice that in this case, I don't have this PD. I don't have this probability of the true because I only have a sample. So I don't need to actually draw anything. I already have the samples. All I have to do is to evaluate this. It's convenient to have it. Otherwise, I cannot carry out that integral. On the other side, if I have a problem where I have the density, right? Then I need to carry out, I would argue that I need to carry out this integral because now I need to sample this function. And sampling this function using the normalizing flow is pretty easy. I cannot use this guy because this guy requires me to sample the true densities, and that's difficult. And so I will use the reverse KLD because I can sample values of x from the normalizing flow, and literally, even 1 million dimensional degrees of freedom can be integrated instantaneously as this. So depending on what problem you're in, you only need this. Now, there is another conceptual trick here that is important when we implement the normalizing flow. Recall that we have to go and try to update the weights and biases of the S and the T's that are buried the normalizing flows. That means that if this is the loss, we need to take the derivative with respect to the weights and biases and go over the derivatives of all this full thing. Now, there is a derivative of the P function as it is, but because x's are sampled from the normalizing flow, they are directly connected with the computational graph, which means that you need to keep these two terms when you use these laws. So when we will do the example and code it up, you need to have both of them. The other cool thing about this is that the true distribution doesn't have to be normalized, because a normalization of, imagine that this function is written as its norm times an unnormalized density. Then in this logarithm, that appears as a constant. And optimization of normalizing flow only cares about the derivative. So in the derivative, that piece doesn't play any role. And that's why we can optimize any density, even if it's not normalized. For instance, differential cross-sections, they are not normalized as it comes from theoretical frameworks. Of course, you can normalize it by integrating it and then divide it, but you don't have to for the purpose of this. For the cases where you're playing with the samples themselves, notice that the true density doesn't exist because you don't have this guy in hand. But technically speaking, you don't need that because the derivative is not connected. These samples are never connected with the weights and biases. So if you take the derivative, this piece is technically a constant and you don't need it. So all you need is minus log of this guy to optimize. And so that's why, depending on the problem you have, you either use the reverse KLD or the standard KLD. And the literature really sucks explaining that. Yeah.
So is it just a Monte Carlo rule that if you randomly sample points from a probability distribution, that's the same as just those points? Like xk is equal to the probability of xk?
No, so this notation means in statistics that you are sampling samples of X from this density. This is not saying this is equal by any capacity. This,
You're given a probability, you randomly sample points, and those are,
no, this doesn't mean the algorithm per se. This means that this X is drawn from this density. What do you use to generate those samples? That's up to you, but this is just a mathematical way of expressing I am drawing samples from this density. In this case, I'm drawing the samples from the true, but I don't have the true because nature somehow gave me the cat's faces already, and I don't need to know what's the probability density for the cat faces. Does it help? Okay. All right. So how do we code it up this? So the only thing that you have to do for the reverse KLD will be you have to ask the model that you coded up yesterday and say, give me a batch. So give me, let's say, 100 examples. Then it will return for you your samples and the associated log probability. You can take these samples and feed it into a target probability that you might have here so that you can evaluate the true probability associated with this. And you compute this distance, the mean, and this is your loss. So it's just 3 lines of a code to construct the metric, a very simple one. For training the normalizing flow on samples, that's a little bit trickier. What you have to do first is to first take the data that you have, right, this data, feed it into the backward model so that you can go back all the way to the Gaussian initial point. So you have to do the inverse transform. And then you have to feed it into the forward to be able to get the corresponding samples and the normalized slope is with the associated log, and then construct the log probability. And as I said, you only need to actually minimize the minus of the log fake. So you can see that the loss function is different depending on the 2 cases. Okay. This is more complicated. I'm going to play with this guy here because probably this is very useful for anyone who wants to connect your beautiful theory to experiments. Okay. What happened? Oh, I went backwards. I went backwards. No. I feel like it didn't erase some of the slides. Sorry, I will clean up later, okay? Okay, so as yesterday, coding time. So you have already your normalizing flow. So I assume that you can decide the dimensionality. And what I want you to do is to code up a target density. So imagine that this example is essentially a 2-dimensional problem. So it's just a 2D problem. We are going to generate two Gaussian peaks that are sitting at -2, -2. And sorry, at 2 plus 2, 2,2. And then the other one is sitting at -2, -2. So 2 Gaussians. So that's the associated probability. You sum basically the Gaussian, the 2 Gaussians, and you take the log. That will be the probability associated with 2 Gaussians that looks like, actually it should look like this. Okay, so I have an analytic function for the PDF, and this problem falls under the class of problems where you have the probability to begin with. So also because we want to also play with the ground truth, it's very simple to generate samples of two Gaussian peaks. So here is the sample code that you can use, and you can instantiate this target class. And you can, if you evaluate, you can see a bunch of numbers here. You can see that this is corresponding to the first peak, this corresponds to the second peak. And if you use this chunk of a code to be able to make a histogram. It should look like this. Okay. So what I want you to do in the next maybe 10 minutes is try to use the code that is here to train again, to train that normalizing flow to this two-dimensional Gaussian. So here is the setup. So it has to be a 2D problem. I set it to 100, a batch of 100. I put 10 flows, initialize all the 10 flows, chain it into a normalizing flow class, instantiate the target distribution that I want to mimic, instantiate the optimizer. So this will be the first part. And then you follow up by this part. Remember, we are going to do, let's say 10K iterations for the training. The first step is always wipe out the gradient, generate samples from the normalizing flow, compute the true probability, because as I said, we are working in the class where you have the true probability, compute the loss. And please try to use this guy. This is a very useful trick. If the loss becomes none, or if the loss becomes infinity, that means that that region is, that gradient is not interesting. So you should not try to optimize anything there because it will fail. And all I did here is just to give you another set of code here, just to see the sort of the training loop and so on and so forth. And if things works well, you should be able to see a loss that goes down like that. And this is sort of the behavior of your normalizing flow with two peaks. And this is the ground truth. So spend maybe 5-10 minutes and I walk around if you have any questions. Yeah, go ahead.
D is the dimensionality. I think I got that down. Number of flows. I think I also have. And batch is what again?
Batch is so the batch is defined here as 100, right?
Right.
So what you're going to do is you're going to query the normalizing flow 100 times. So what does that mean technically? It means that internally there will be 100 Gaussian samples generated from the base density that get converted to the flows, to the final space that after 10 flows you live in a different space, but it's still still two-dimensional, and you have. Let me just try to draw graphically. That might be easier. So, this is the base space. This is your target space. And so what the normalizing flow will do is we'll poke, let's say the batch was 5. So it will randomly select 5 points. These 5 points will get mapped somewhere here, right? Let's say it was something like this. And it will then evaluate the log PDFs to be able to match with the true PDF. And that's about it. So if you have bigger batch, that means you want to sample more. So the bigger the batch is, the more accurate your gradients are to move the weights and biases of the normalizing flow. Okay. If you have only few, then that will be problematic because you are going to poke the parameters, the data space only few. So imagine that this is like a 1,000-dimensional problem, right? And then you just do a batch of 2. Yeah. So that will be hard.
So I guess maybe what I was missing is, so batch seems like the number of like points you're sampling, I guess. I guess I kind of thought that's what the number of flows was. So
No, number of flows is, so this is X. And we are going to go internally to, let's say, Y1, Y2. In each case, this is 2-dimension, 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 down to this space, let's say Y10, which is still 2-dimension. The flows is basically the number of affine coupling transformations that you put to, to enlarge the expressivity of your normalizing flow.
And the loss / gradient occurs for each of the flows.
Yes.
Okay, so 10 flows means essentially 10 steps trying to get from random point to good point.
Yeah.
Okay.
Each flow has its own S and T's, neural nets.
And for each batch, each one of the 100, you you get a
No.
new weight.
No, you don't. So
Each point, they use the same weights?
it would be the same weights and biases in the neural net.
For each point or for X to Y1 to Y2 to Y3?
So there is an affine coupling that is defined by a fixed state of S and T.
Yeah.
So for each transformation, you have an S and T. From here to here, you have another S and T, right? And these guys are frozen regardless of what input you put. So you pick this guy, it will transform into this guy with the same S and T. If you select this guy, it will transform to with the same S and T to a Y1, to another Y prime. And you keep doing this thing through all the flows.
If it's the same S and T, will it be a different Y prime because it's a different X?
Yeah. All good? No good?
Change the degree.
Yeah.
Like this.
Yeah.
Copy this, but I'm getting. Visualization takes 2 positional arguments when 3 was given. Giving too many. Those are dimensions, but it seems like so.
Okay, but you need to first sample, right?
Where do you define?
So maybe what I didn't put here is that you need to generate the Y. So sorry, I should have put here a line.
It's like coordinate.
But where is the Y coming from?
Okay.
Yeah.
I think I might
You
have
need
missed
to,
some.
you need to initialize. So here you need to put a line
No.
that says target equal target. It is there, I don't know.
This one, right?
Yeah, you need that.
Okay. But
Right.
I don't know, actually it was showing that you have too many.
Maybe it was here. Maybe it was here, this guy, yeah.
Yeah.
You instantiate it without having the class, and now you can class.
Sorry, I didn't, you copy by hand, right? I didn't.
Oh.
didn't. Yeah, you need to initialize.
That is maybe there.
Yeah. Hopefully, yes. Just
So basically 1 and 2 were the changes.
because in the code I am resampling the calculation every time. But you only got one peak. Oh no.
Yeah, I was.
Is there,
Yes, you.
So you don't
I also got one.
Exercise.
One peak, right?
They're
So
Basically,
try it again.
We can
one quick hack to get something like that, something like this, is to enlarge the standard deviation. And I think that that will help. That you can do here, I put like 0.3, just put like 0.5. So that this guy becomes a bit bigger. And that means that the distribution is a little bit easier. So part of the difficulty is that you are not going to always nail the distribution perfectly. There will be other metrics that needs to be in place. But for the time being, in order to get something like this, try to enlarge the density or run it again, and maybe the model will not collapse.
Okay. Is the thing is that I tried to.
Yeah, just put 1,000. 10 points is too tiny.
Okay, and here is except for this one.
Yeah, so this is the ground truth, but I think the model has failed.
What is it?
So let's do one thing. And the plan and the number 5. And let's run, start like this. What's the execution?
Okay, something.
I think you can, yeah, you can click here,
Yeah.
stop it, and let's try to run this guy again. Yeah.
Maybe.
Okay.
Oh,
These were the two options, like previous ones.
Yeah, he's
What does
here.
this?
No, this is fake, or this is the true.
Now we have to run distribution. Here's the thing that it's fake. Distribution.
This is doing that.
Yeah, so this is better, but it's moving into only one big.
Yes.
Yeah, I forgot that to mention, sorry, there are too many things that I wanted to tell you, and I forgot one thing. Let's see.
This inside this.
So,
The evolution of the.
so quick thought, quick hack. There is a quick hack to solve the problem of that. One of the suggestions that I found in the literature is to make the transformation to be identity at the beginning. Okay. So how do I enforce that the transformation is a Gaussian at the beginning? So identity means that this thing here becomes identical to this. How can I in principle enforce that?
Yes.
Well, the answer is very simple. Set S to be 0 and set T to be 0. And there is a way to make that thing happen because you know that this S is just a simple neural net, right? Did I have the S somewhere? Yeah. Right, so there is a layer that goes in between here to map. And the trick is to set the weights and biases of the last layer of S to be 0. So that is something that I have somewhere here. Let's see. I'm going to copy this thing somewhere in the slide so that you can see it. Going to put it down here. Oops. So if you put these lines uncommented out naturally, okay, you can put these guys essentially around here after this. So once you do this, you can write after that, you can put those lines that I just said. And what it's doing is telling Torch, set the last layer, the weights of the last layer, and the biases of the last layer to 0. So when you do that, when you start seeing, in the training epoch 0, what you will see is just basically a Gaussian centered around 0, because all you're doing is going for a Gaussian to a Gaussian. And I think that will help in principle to create these two peaks, because if at the beginning the distribution is kind of squeezed around this guy, then everything will gravitate towards this guy. Okay. Who has some success or partial success? Do you guys see something like this? At least half of it? Who saw the two of them?
Yeah.
You saw the two of them. More or less two?
Yeah.
Two?
So she's in recovery.
So
Has she taken a visitor?
it's happening.
Showing something, but not exactly like loop.
Okay. So I think that you can play more up with that just by increasing the number of flows. That's one possibility.
Thanks, bye.
The other thing that you can do is to decrease the learning rate, because one of the issues that happens is that if we start training with a very high learning rate, then it collapses with a quick, it's kind of lazy, so it will try to get quickly to, yeah.
So we can say that in general, also this method has problems finding isolated peaks in the distribution.
Right, so your prior space has to be wild. So since we have the ability, so I didn't play too much about changing the base density. You can enlarge the base density. So imagine that your base density at the beginning is a tiny Gaussian around here, right? Then the chances that it will go to here will be large. But if you make the Gaussian to be at the beginning like a gigantic, then the ability to land either on this or that is higher. So it depends on kind of in your prior setup. Yeah.
Some weird stuff, so I don't know what's happening.
Mine did the same thing, I just restarted it.
Yes, restarted it. Did you guys include it? Or you copy the code? Yeah, sometimes it collapses. And it's frustrating because I want to do it only once. But okay, I don't have a perfect recipe. I just have a lot of patience to do it in a row.
I guess maybe can I get you to explain one more time? Well, I guess I was confused on why you set the last layer to zeros. But
Yeah.
then you said something like taking it from a Gaussian and then leaving it as a Gaussian.
So if S and T is 0, the transformation is an identity. So-
But if it's the last layer, like you wrote here, you start at X, then you go Y1, Y2, Y3, Y4.
So if the last layer of S, if the weights and biases of the last layer of S and T are 0, the output of S and T are also 0. Because recall that by construction, the last layer,
Which means at least 2.
the last layer will be multiplied, there will be an input features multiplied by the weight matrix plus the bias.
And when they were zeros, it just outputted the same.
It will be 0. Regardless of what it comes, it will be 0. So you can impose no changes or unit transformation at the beginning of the training by setting the last layers to be 0. I saw another question. You see our question?
Oh, yes. Well, like mine first for a second, I see like one.
Yeah, so you can decrease the learning rate. So it's better if it goes slowly.
Gives a random.
Yeah.
Oh, I see it.
Now it-
Wait.
I like almost get that, but it's like the Gaussian distribution. So a random point along the Gaussian.
Okay, I see a really good one there. Really good one there. Let me take a
Around.
Somehow it was really good or bad, I don't know.
Y1 and Y2
good or bad,
just values.
you manage.
That are sample. I have infinity somewhere.
Okay, say it again.
I have infinity somewhere.
You have infinity.
Oh, sample.
Okay.
That's what, say all those lines. The init 0 or value.
So where?
Yes.
So you have to put them in the flow class. Just right after, once you declare this, you can put it here. Because that will enforce that when you initialize this, the last layers are set to 0.
It's part of the constructor.
Yes, as part of the constructor.
Yeah, this is Gaussian.
So that would allow you to start not from a random shape and more like a Gaussian, uniformly distributed.
Generate all.
Okay.
These are just any random point.
Yes.
Any random
The
flow.
bottom of the function.
This calls here, Y.
Like at this indentation level, and then you just put it here.
Oh, okay. At the indentation of the function.
Yes. Technically, this is a function, but it has been instantiated, right? So just put it on this indentation.
Oh, okay.
And then which of
It's like, what?
flows?
Yes.
That's CFNS.
Like what? I guess I don't get the point of the first block, like from,
Who has finished more or less?
why do we need to go here? We're just a Gaussian. We can-
Let me ask again, who has finished? 1, 2, 3-ish, 4-ish.
This is still weird.
Okay. But it's, oh,
It's still.
okay. Okay. So I need to keep going. I'll let you play more bit later because I want to tell you another story. Is that you can see that all this stuff that I told you in the last day or so is kind of crappy because even I'm showing you something that doesn't look like this, right? And there is this region here that appears no matter what you do. And even the most experts won't be able to get rid of this by hacking the normalizing flow code. It doesn't depend on the number of flows. It doesn't depend on how deep you want to make the S and the T's. That stuff, it won't disappear. I am really not sure or understand the logic behind that. The only thing that I read is that this thing here has a different topology with respect to one Gaussian from the base density that has one topology. So the base density for us is a Gaussian. And we want to go into two Gaussians that are disjoint. And that is topologically inequivalent. So the normalizing flow has a trouble by construction in changing some topological behavior. And so at that moment, you can say, well, why did we spend an hour doing this crap if it doesn't work at the end of the day? And it turns out that we can actually fix the problem, not by improving the normalizing flow. And moreover, it really doesn't matter if your normalizing flow is crappy. That sounds like counterintuitive. But all I'm telling you is that in this game, you don't need to have a normalizing flow that is perfectly trained. You don't need to have a normalizing flow that is not perfect and has this thing, because we know how to correct this mistake very quickly in a very cheap way. And so that brings me to this concept of Markov chain Monte Carlo that people in lattice QCD normally use a lot. How many of you understand Markov chain Monte Carlo? You, less than a half of the group. So let me walk through it, the basics of what you need to do. normally when you go and read Markov chain Monte Carlo, there's a bunch of theory thing, and I'm not going to tell you about the theory behind that. I'm just going to tell you what you need to know how to implement it so that it makes sense. So the Markov chain Monte Carlo is a chain, and this is my cartoon of a chain. The chain can be as large as you want, okay? And what we want is essentially to populate in these blobs in the chain, we want to populate the samples, okay? So here are the normalizing flow samples. Suppose you have your model that it was semi-well-tuned with the imperfections. And now you generate samples, and these are your samples from the normalizing flow. So I'm going to tell you the recipe to construct a Markov chain out of that. So the first thing that you have to do always is you have to start with one state. So you will take the first thing that you obtain and copy and paste here. And that will be the first entry of your Markov chain. So you have to always start from somewhere. And that's the way to start. Just copy the first thing that you saw. Then in the next step, you are going to take the next sample as the proposed state, okay? And we will decide whether this guy will go here or not. And so cartoon-wise, it means that there is something that it will dictate whether or not this guy is going to be accepted or is going to be rejected. So there are two possibilities here. It's either accepted or rejected. So if it's accepted, then this guy is going to be copied to this entry, naturally. The part that people get confused, or I personally got confused many times in the past, was what happened when you rejected. You might think that rejection means just go to the next one to try to fill that, and that is not true. That is absolutely not true. If you do that, it will fail. I learned in the hard way. So you have to, if this box here decided to reject, then what you're going to do is you copy the previous state. That's how it works. So either you take the proposed state and put it here, or you copy the previous state. That's how this accept and reject translate into. And if you don't follow that rules, then you violate an entire theory of Markov chain Monte Carlo that I'm not going to tell you about, but that's the reality. So you can keep doing this. So let's say the next proposed state, this was accepted, so it's copied. Maybe the next one is also accepted, is copied, and you keep doing that. Sometimes it will be replicated, sometimes it will be copied, and so on and so forth. And the statement is that this thing here is asymptotically correct. That means in the infinite sampling, that's the theorem, this sampling algorithm correctly generates the samples of the underlying PDF. That's the theorem. Now, of course, you might imagine what happens if you start copying the same thing over and over and it's never accepted. That means that all these samples here are kind of crappy, right? And then you can have a chain that is a billions of sites, but it's the same thing. So that is a measure of the acceptance rate. So you can actually count what is your acceptance rate. At the beginning, your acceptance rate is 1. Then once you go to the second state, you can count how many was rejected versus how many you have. Well, 1 was rejected, so your acceptance rate is 1 divided by 2. Then you go to the next, this was accepted, and so how many got rejected? Still only 1 divided by 3, so your acceptance rate, so it's the opposite. How many has been accepted? So the game of this is to maximize your acceptance rate. That's one of the metrics that people use to see how efficient your sampling is. So you can see that if you train your normalizing flow absolutely garbage normalizing flow, it is likely that you are not going to accept many samples. So your acceptance rate is very low. But if you tune your normalizing flow absolutely perfect, then you are going to accept everything. And you have a perfect sampling. So the trade-off is depending on your problem, depending on how much enthusiasm you have, you keep training. And once you are kind of, okay, bulk part okay, you can just correct the mistake of your normalizing flow by the Metropolis-Hastings algorithm, which I haven't told you. What is it? What is this box that decide to accept and reject? How many of you have ever done this exercise of computing pi by throwing dots into a circle? Good. It is essentially the same thing. It's no different from that. So the algorithm starts by doing some labeling. Since this is the proposed state, we are going to call y new. And this is the old state. The immediately old state is called the old state, y old. So what you have to do is to set, is the following. The first thing is you are going to compute this quantity. It doesn't really matter the name. We call it ACC. And it's the minimum between 1 and this guy. So normally, in traditional Markov chain Monte Carlo, for those who knows that, the proposal function is a Gaussian, which is symmetric, and this term actually doesn't exist in traditional Markov chain Gaussian-based sampling. This doesn't exist because it's a symmetric function. But when you have a normalizing flow as a proposal function, this doesn't cancel out. So you actually have to have this weight here to reweight your true probability ratio. Okay? So this is what you have to compute. And let's think about it. Can I compute the true density and the true y new and true old new? The answer is yes, in the context of where you have a problem where the density is given. If I want to do this thing with cat faces and dog faces, I can't do it because I don't have this guy. So this Metropolis Hastings step to fix the normalizing flow is only for the cases where you have the density. And can I compute the probability for the fake? Yes, because by definition, the normalizing flow is giving you that. So once you compute that, what you do is the same story about throwing dots on the circle to get pi. You accept or reject, right? And so you are going to throw a random number uniform between 0 and 1. And you are going to decide to accept. If this number is less than the accept, you will call this state to be accept. And if this number is greater than the accept, then it's outside of the circle, so it will be reject. That's it. Okay, so here's a collapse symbol. And I just gave you here a simple Metropolis Hastings step so that you can go and curate your normalizing flow. So I assume that you have trained your model. So you have your model that has been trained. And what you're going to do is to feed this model into the Metropolis Hastings step. Maybe a couple of things that I should tell you. Because you want to not train, you don't need the gradients anymore. Therefore, it's instructive to switch off the gradient scheme here. So that's why we have this with torch no grad. And all you do is to generate samples from the normalizing flow. Because some of the samples are going to be lost, you are going to oversample. So I just put here 2 times the number of samples that I want. So you construct the samples, the probability, go ahead and compute the true probability associated with that. And then here, you just basically build the chain. And I will let you go to the lines by yourself. But what I wrote here is identical to what I just said in a few slides before. And then you just feed the model, give me 10,000 events, give me the acceptance rate, and also give me the chain. And from the chain, you can start plotting. So I will give you another 10 minutes or so to deal with it. No, I'm not using the slideshow. It should be like this. Any help, any assistance, just raise the hand. I will stop by and help you out. And also, if there is a bug in any of things that I just said, let me know. I'll fix it. Ah, or we have a meeting at 4:30. Pick the thing with Marco. Ah, can you tell that we are? Anyone who feel like it's getting stuck? Everyone is writing all good? Stuck or not stuck? Accept or reject? It was in my code or? Okay. So you see, you started from something that is not Gaussian. So if you do that trick. Oh, you got it, yeah. Then you should start like a gigantic block.
Changes the, so just about change. Plotting code. Instagram, where it's plotting the fake, it just replaces chain.
So in my case, I get something like that. So this is the true, this is the fake normalizing flow thing, and this is the Metropolis Hastings step added. And you can see that now it's identical. And as I promised, I can correct it. Who has reached to this point? 2. All right, let's increase the acceptance rate. Yes. Success. Kind of work. So you can also kind of evaluate the acceptance rate. So if your acceptance rate is too low, it's too bad. So that means you have to tune more the normalizing flow until you get higher acceptance rate.
What's a good acceptance rate?
So if you get the normalizing flow to get 100% acceptance rate in lattice QCD, you will get the Nobel Prize in computing. And you have actually solved QCD if you can get that. So MIT group, this most of this I learned this thing from the MIT group that are trying to make it work. And they can enlarge the acceptance rate, but seems complicated because you have to burn a lot of compute power. And so there is always a question, are you really spending more time on tuning the S and the T's versus really making more, using the CPU powers or GPU powers for making more gate innovation? But back to your question, 80%, I think, is it 80% for Gaussian proposals? Peter?
I don't know.
So it's either 60% is like a classical Gaussian proposal function. So no normalizing flows, because you can generate some proposed states from a Gaussian. And that, I think my understanding is something like a 60% or 80%. I think it's 60%. 80 is too high. And then with normalizing flows, you can bump it up. And that's why a lot of people are kind of super excited. And the people who do inverse problems outside of physics do this. And so that's why I think that is an opportunity that everyone should start using these tools. Seems no-brainer. Okay, in the interest of time, let me move on. I hope you guys managed to implement the Metropolis hasting step. So I don't, because the time is limited, I'm just going to leave you this as a homework. So that because Alexei told me you have to bring something that is connected with the EIC. And so far, I have not given you anything that is remotely connected to the EIC. Well, maybe I have said in words. And so let's go back to things that I know by heart because I get paid by doing this. So a toy realistic thing. So you guys were introduced with structure functions. Yes. People know what is that thing? Okay. So if you apply collinear factorization, someone in this school told you that you can write the structure function in terms of the parton densities using this convolutional formulae, where these coefficient functions can be calculated in particular QCD, right? So let's not make life super complicated. Let's go to leading order. So I forgot to add a sum here. Actually, I don't know why it didn't change. So forget about this. Oh no, I need to have the charge because a leading order, you have to have the charge weighted for each P labor. So there's a sum. So I'm going to go from general to leading order. And let's pretend that there is only one quark, which is a fiction, but let's pretend there is only one quark. And so you get something like this. Right? So this is a ultra simplified problem because I just want to connect with something close to EIC. This is something that experimentalists at EIC can measure. And let's forget about the Q-square dependence. So let's ignore for the time being that we have the graph evolution on top of this. All that complication, let's remove it. You can, removing doesn't mean that you can put it back. You can easily put it back. So I'm just removing that thing for simplicity. And let's say that my parton density is parameterized in some way. So let's use something very cheap, like x to something, 1 minus x to something. Don't need to impose number sum rules right now. This is just to give you an idea that I have something that EIC will measure, just so I don't get into trouble. I'm going to render this problem into a parameterization inference problem, right? So this theta 1 and theta 2 are my parameters. And so here is a simple numerical implementation that you can just check right now as we speak. You can just copy and paste. I gave you also this chunk of the code to make the plot. So all I did here is to cook up a parton density that the first exponent is minus 0.5, the second exponent is 3, so it's kind of divergent at small x, and it goes to 0 at high x. And then I'm going to convert that thing to a leading order formulae into a structured function, f2, that looks like this. And I'm going to pretend that I'm an experimentalist, and I'm going to add some Gaussian noise, put some errors. And so this is what EIC measures. Of course not. I'm just pretending that EIC can measure this, and these are the errors, right? Let's say that we are there. Then one thing that you can imagine is let's randomize the parameters around these values that I choose, minus 1/2 and 3. And if you randomize them, if you plot them, okay, you have a bunch of things that look like that. And so the goal is to do a Bayesian inference, right? And then use the normalizing flow that we just discussed. So in order to do that, all I have to do is to define a probability measure for these parameters. So I just show you the simulation of the data. I have a theory that depends on these two parameters. I put some 10% error. So this is my chi-square function. That goes into the likelihood function as an exponential. Put it here, ignore the pi, no priors. The posterior is just the likelihood, okay? And you can cook up something very cheap in these 6 lines of a code. So now you have your target get log PDF instead of having these stupid 2 Gaussian peaks. So for the remainder of time and whatever Alexei says so, try to work it out because you have all the tools. And if it all goes well, you should be able to generate samples for, sorry, this should be theta 1 and theta 2 that are distributed around 0.5-ish, around 3. You can make a plot of the quote-unquote F2 structure function that it should look like that. And this is the example for how would you use, this normalizing flow for parameter inference. I think that it would be good if you ask me right now, if you have any questions, last minute questions before I hand it over to Alexei. You have any questions? Like conceptual ones, Is this obvious to you now that we can compute chi-squares, compute a probability, and now pass it into a normalizing flow? Is this completely foreign for you?
Must we leave it as a homework or we do it the remainder of the time?
It should be homework.
Should be homework. Should we thank you first and then ask questions?
Okay, thank you for
Let's thank him. Here tomorrow. So if you want to go through this exercise, ask now. Go ahead.
It was not different, but now you have little subsampling in it. Do you need to do some sort of autocorrelation corrections?
So all I did was a very cheap thing. that, basically what you find in Wikipedia, how to correct the sampling. But yeah, I am no expert in Markov chain or even beyond that point. Beyond that point, lattice people invented billions of different things to make it better, as well as statisticians. So yes, you should be put more stuff on top of it. Yeah.
Sure. And also on the example, so in blockchain, to explore those distributions or to sample it better, you don't want an acceptance rate which is close to 1. You actually want one which is less than 1, so you have more exploration steps in the thing.
Yeah, what I mentioned is you need to have beyond the acceptance rate, you need to have the autocorrelation time, monitoring that. Yeah. All the bells and whistles that I didn't say, yeah, it should be in place.
That is
Yeah. It's too complicated for the Summer School. Anything else? If you are curious, you can drop me an email. Hopefully the emails are around there. I will try to keep improving the slides. Apologies that it was a little bit sloppy. I was doing this thing on the fly, more or less. But with your help, I can keep improving so that it could be used for you for the future. If you're like, oh yeah, why not? Let's do normalizing flow. Or it could be useful for future students that I might tell them the story. Anyhow, if there is no more questions, back to Alexei.
Yeah. Get some time for dinner, maybe thinking about some of these things and asking later today. Okay. Adjourn then. 7.
Take me now.